See here, the first one, this is related to the recovery voltage after fault clearing. Once a fault is present in the system, when you clear the fault, how the system will try to recover. So the voltage is given in terms of per unit in the y-axis, and the x-axis is the time. The time taken to recover the voltage after fault clearing. This is a time will be taken to recover your fault there. And the second one, this is with respect to the fault initiation, when the fault is initiated within the power system. So in that case, you look at that how the voltage per unit voltage will be varying there with respect to the time. And finally, this one, the figure C, this is the over voltage at the line end after fault clearing. Once you clear the fault, at the end, we have a sending end and receiving end, we used to say. If this is a Vs sending voltage and this is a Vr receiving end, okay, at this end, once a fault is cleared in this line, I am clearing this fault. Okay, when the fault is clear, the voltage, the over voltage at the line end, it will be in this fashion. So this is a over voltage is going to happen within the line. And the figure D, which represents the energization of long transmission line, but charging of transmission line. Suddenly I am adding a new line. I am charging the line after maintenance or any new line which has been added, right? So in that case, this is a sudden increase in the voltage is going to happen. You can see here the voltage is very, very high. Almost 3 per unit voltage, the peak will be there. So finally, the last one, this is a over voltage at the end, at the line end during your this case. When I added a new line, okay, at the end of the transmission line, assume this is a new line, okay, assume this is a new line. After adding this line, this is a voltage is going to appear. At the end of this voltage, VR will be in this way. It won't be a constant. It will be varying for a few microseconds over there. Sorry, milliseconds. So this is a voltage at a line end once you charge a new line. Okay. So these are few figures which will show that how your waveforms are irregular, right? Which are not having a constant waveform shape, which are irregular and which can be with high frequency and power frequency within the power system. In few cases where the over voltage is about 2.4 per unit, in few cases, and in few cases 2.4 per unit, and in few cases transformer energization. In other cases, we may have 1.4 to 2 per unit voltage will be increased in the transmission line due to the switching. So next is the switching over voltage in extra high voltage and ultra high voltage system. What happens when the switching is done and how this over voltage will be generated in extra high voltage and ultra high voltage system, because this is very, very important whenever we are using a long transmission line with very high voltages. Okay. Who is that? Contribute yourself. So here the insulation has a lowest strength for switching surges with regards to the long air gap. So the insulation has the lowest strength of a switching surge with regards to the long air gap. When you take a high transmission line, even though if I am maintaining a gap between two conductors, whether it's a DC, whether it's a AC, if you're maintaining a long distance of air gap, the insulation will be having a low strength in these cases. And these switching surges or switching over voltage are relatively higher magnitude, right? These switching surges will be having very high magnitude as compared to the lightning over voltage for extra high voltage, sorry, ultra high voltage system. So just look at this point here. So whatever the voltage will be appeared in the power system due to the lightning, so we know that the lightning has very large, huge amount of power, right? So whereas the switching will be having very high magnitude when compared to the lightning. They're saying that the switching surge is having more power compared to the lightning over voltages here with respect to ultra high voltage system. and the over voltage are generated in the extra high voltage system because of these many reasons here. That could be because of sudden release of your internal energy stored within your system, because there are many such equipments within a power system. The charge will be stored, so these charges will get discharged, internal energy stored, which will get discharged in the form of electrostatic form in a capacitor or electromagnetic form in a inductor, right? So because of this, there are different situation which happens or where the over voltage will generate within a extra high voltage system. Or the first one, interruption of low inductive current by high speed circuit breaker. Interruption of low inductive current by high speed circuit breaker. So this will occur when a transformer or reactor is switched off. So there will be a low inductive current and high speed circuit breaker will be operated. So whenever I am trying to switch off your transformers or reactors, in that case this will be going to happen. The second one, interruption of small captive current. So this is because of whenever there is a, we are trying to switching off unloaded lines. Even though we have a transmission line, if there is a no load or no feeder is connected to that transmission line, in that cases what happen, there will be a interruption for a small capacitive current. And the next one is a ferro resonance condition. So this may occur when poles of circuit breaker do not close simultaneously. We know that we'll be having a 3 poles R, Y, B, right? So different line will be having a different circuit breaker. So whenever I want to operate a circuit breaker, so the opening and closing of the circuit breaker should happen simultaneously with respect to all the phases. So there are few cases what happen, the poles of the circuit breaker will not close simultaneously. Because of that, the ferro resonance condition will lead to the over voltage within a extra high voltage system. And the next one is energization of EHV and UHV lines. So when you are trying to add, when you are trying to charge your lines, new lines, so in that case also we will be having a over voltages. And there are a transient voltage also will be generated within the power system based on the above cases which has been quoted there, because of your low inductive current, because of captive current, ferro resonance condition, or energization of EHV and UHV. So the transient over voltage will be generated in the order of 2 to 3.3 per unit. So I'm talking in terms of per unit. So this, what do you mean per unit? So these things will be going to study in the next semester in the PSS subject. So where instead of saying 440 kV or 440 volts, we may say 1 per unit. So 440 will represent as a 1 per unit. Anything less than that, 0.7, we say if it is a 0.7, then it is not 440 volts. Okay, it is less than that. So in that way, we represent that in terms of per unit. We will see in detail about why we need to go for per unit indication. What are the advantages of those? We'll be studying in the next semester PSS subject. So where the voltage will be in the order of 2 to 3.3 per unit, and will have a magnitude of order of 1200 kV to 2000 kV on 750 kV system. So that is nothing but almost an extra high voltage system. So this is my extra high voltage system, 760 kV, 750 kV. And there are a few other situations of switchings which will give rise to the switching over voltage of short duration of 0.5 to 5 millisecond, and with a lower magnitude of 2 to 2.5 per unit. So because of these cases, when your single phase closing is happening of a circuit breaker, I'm trying to close a single phase of a circuit breaker. So even though the phases are three phases, I'm trying to close only one phase. In that case also, so there will be a switching over voltage will be present, which will be magnitude of 2 to 2.5 per unit. And because of interruption of fault current, so that is when we have line to ground fault or line to line fault, So this fault, whenever it is the system, the fault are present within the system, when you try to clear this fault, I'm clearing a line to ground fault, I'm clearing a line to line fault. So during this, there will be interruption of a fault current because there is a fault, I'm clearing the fault now. So the fault current won't be same because it has to settle down, right? So initially there may be a oscillation. When you clear the fault, it has to settle down. So in that case, there will be interruption of a fault current. So this LG fault that we call say symmetrical fault or unsymmetrical faults. So this concept also will be studying in the next semester in a PSA subject, power system analysis subject. The next one is resistance switching used in circuit breaker. So there are few cases they make use of a resistor to limit the current which is flowing within a circuit breaker. That is called resistance switching. And switching lines terminated by transformers. So there are a few lines. If you take a transmission line or a distribution line, and your distribution line will end with a transformer, there is nothing else connected to that. In that cases, if you have a switching lines terminated with a transformer, the line is terminated by a transformer, no load connected to that. In that case also we may have this situation. We will be having a lower magnitude. And series capacitor compensated lines. We make use of a capacitor to compensate the line for a reactive power compensation to improve the power factor, right? In that cases, we make use of this. In that cases also, it may lead to the lower magnitude. And finally, the sparking of surge diverters. So we know that already we have been discussed in a testing of surge diverter or lightning arrestor, both are same. So whenever the spark is occurred within this surge diverter located at a receiving end of a line to limit your lightning over voltage. So whenever the spark is occurred, in that case also we may have a lower magnitude of a voltage in the power system. These are the few cases why the lower voltage or lower magnitude of voltage will happen within a power system. So next is the over voltage due to the condition which was studied here. The reason of over voltage or lower magnitude with a short duration. So with that condition, we can calculate how this over voltage can be calculated using three methods. The first one is we can make use of a mathematical modeling of a system using a digital computers. We can make use and we can do a modeling. So that we will be studying in the probably in the 7th semester, where we have this PSA laboratory where we do this analysis. We plot, we draw the circuit. We take a transmission line. We take a generator. We take in loads, and we try to do the analysis, mathematical modeling of the system, and we try to determine what is a fault current, what is your line current. So all those will be done with help of a digital computers, where we have a software called as a My Power package. That will be doing the experiment in the 7th semester. That is one of the method for a mathematical modeling. And the second one is scale modeling using transient network analyzer, and by conducting field tests to determine the expected maximum amplitude of over voltage and their duration at different points on the line. So we may go with two tests, which is mathematical and scale modeling. Another, we can go directly to the line physically and we check what is the reason of over voltage, what could be the maximum over voltage will occur. We can record that, we can measure, and what is the duration taken to rise this voltage and how long this over voltage will be present within the transmission line. We can be monitor that. So these are the three ways to calculate the over voltage for these conditions. So next is the main factors that are investigated in the above studies while doing your calculation, modeling, mathematical modeling or field test or your other mathematical modeling. In that cases, we need to investigate that main factor we need to investigate with respect to those points. The first one is the effect of line parameters. Like it could be what happens when you connect a series capacitor, what happens when you connect a series shunt reactor on the magnitude and the duration of a transient. If I add any resistor, if I add any capacitor or if I add any reactor, okay, what happens to the magnitude of duration of the transient, whether it will increase or it will decrease. So obviously when I say over voltage, you'll be having a high magnitudes. If you connect any reactors, okay, in that is in with respect to shunt, if I connect a capacitor in series with respect to this, whether this magnitude will vary or not, how it will gonna vary, magnitude as well as a duration also, at what time it will settle down. So that investigation will be done over here. That is the first one. The second one, the damping factor, which need to be needed to reduce the magnitude of over voltage. So we make use of a factors while doing a mathematical model. So similarly, we have problems which will be solving in the 7th semester in the PSA 2 subject, where we make use of this constant, which will lead you to do the iteration very fastly, so that I can settle down the time required for your fault clearance. So that is a second parameter. And the third one, the effect of single pole closing or restriking and switching with a series resistor in a circuit breaker on the over voltage. So within a circuit breaker, whenever there is a single pole closing is happening, instead of all the 3 poles need to close simultaneously, if one pole is closing and the restriking is happening. Restriking means to say it will try to close and it will try to open continuously. It has to be done only when the fault is occurred, but repeatedly it will be restriking. The pole will try to close and try to open. So restriking will happen. In that case, and also while the switching, when you are doing the switching of the series resistor added to the circuit breaker, in that case also we need to study what happens over there. And finally, the lightning arrestor spark core characteristics also need to be studied in detail. So these are necessary things where we need to study with respect to EHV and UHV system to control your switching surges. If you want to control the switching surges to the safe value, when I say safe value, it should be less than 2 per unit. So the magnitude of your high voltage which is generated in the power system should be less than 2 per unit or 2.5 also we can say. So within this it should be present 2.5 per unit or 2 per unit. Mean to say, if I am giving 100 volts for example, it can go maximum of 200 volts or 250 volts. 200 volts will indicate 2 per unit and 250 will indicate 2.5 per unit. So that is a maximum 2.5 times of the voltage can be increased. I need to limit that by controlling all these parameters. So next one is, what are the measures to be taken to control or to reduce the voltage? I said that it should be less than 2 or 2.5 per unit. Now what are the measures to take to reduce that your voltage to less than 2 or 2.5 per unit? So there are basically 4 steps. In the first step, we say multi-step energization of lines. Instead of adding one line, you add multiple lines. You charge multiple lines simultaneously. That is also one method, because the over voltage will be distributed. It won't be within a single line, right? That is the first case. In the second case, so that should be phase. In the second case, it is a phase controlled closing or circuit breaker with proper sensors. There should be sensors present. If one pole is closing or not closing, we should get a feedback so that we can reinitiate to close that circuit breaker of individual phases. So there should be a phase controlled closing or circuit breaker with a proper sensor. That should be taken care. And the third one, that is drainage of trapped charges, as I mentioned in the previous point. So in the power system, there are many operators which stores the energy. Even though if you discharge the line is in off condition, we cannot touch any equipment because the charge will be stored. I need to discharge that. That is a drainage of a charge which is stored within a transmission line before reclosing of line. If you close the line, suddenly what happened? Already you are giving some voltage, the charge is present over there. So that will add up, and once again the over voltage will lead to go beyond 2.5 per unit. So for that reason, we need to discharge that. This practice we have in the 7th semester laboratory, where we will be doing one of the experiment. In that case, for each trial, we will discharge the charge which is present in the that sphere gap and the transformer, high voltage transformer, rectifier. So we'll be doing practically in the laboratory in a next semester. So we'll understand what is the importance of that. So here we are doing for our safety purpose, but in the transmission line, they do the in the point of to reduce your over voltage. If you're not discharging, if you're not drainaging the trapped charges, that will add up with a when you charge any new line. So voltage will double there. And finally, limiting the over voltage by using a surge diverters. We have a lightning arrestor or surge diverter where we can make use of that. Whenever the over voltage is present there, it can easily divert to the ground without harming any of your other power system components. So if we follow the first three methods, A, B, C method, then we can easily limit the switching surges between 1.5, sorry, we can limit between 1.5 to 2 per unit. If I follow first three steps carefully, I can limit my over voltage between this range. If not, it will go beyond this, then it will lead to the cascading failure. Multiple problems will be created in the power system.